Welcome to the part B of the Data Engineering Masterclass. In part A, we understood the foundations, but now we are entering the real world of data engineering. This is where companies process billions of records, where systems need to scale, and where architecture matters more than just tools. This is the part where you stop thinking like a learner and start thinking like a real data engineer. Hey everyone, welcome back to Pratt Tech Academy. I'm Imran Khan. I bring close to 20 years of experience across data engineering and product management. I've also spent more than a decade at Amazon working on large scale data engineering and product systems. So, in this masterclass, I'm not just going to explain concepts theoretically, I will help you understand how these systems are actually used in real companies. And if you are new to the channel or if you haven't watched Part A yet, I highly recommend watching it first because Part A covers all the core fundamentals step by step. I've added the Part A link in the description below. Once you complete that, this Part B will make a lot more sense. So now let's continue the journey. In part A, we saw how data flows from source systems to ETL pipelines to warehouses to dashboards and analytics. But let me ask you something. How does Amazon process millions of orders every single day? How does Netflix recommend movies instantly? How does Swiggy track deliveries in real time? The answer is not just coding, it's architecture, it's scalability, it's distributed systems. And today we are going to understand the actual systems behind modern data engineering. We will cover Lakehouse Architecture, the big data framework, batch versus real time processing, cloud data engineering, Medallion Architecture, and orchestration concepts used in real world pipelines. So, by the end of the session, you won't just understand tools, you will understand how modern data platforms are designed. So, with that, let's start with one of the most important modern concepts, lakehouse architecture. We already know data lakes, we already know data warehouses, but companies face a huge problem, too many systems, too many copies of data, too much cost. So, companies asked, why not combine the best of both? And that's how lakehouse architecture was born. A lakehouse combines flexibility of a data lake, structured analytics of a data warehouse, meaning you can store raw data and also run analytics on the same platform. Do we need separate systems now? No, exactly. Think about Netflix. When you open Netflix, recommendations, continue watching, trending content, viewing history, all of this uses the same underlying data. Instead of moving data between multiple systems, Netflix can analyze directly from a centralized architecture. Now think about Uber. Uber collects GPS data, driver activity, ride requests, payment transactions. Some data is raw, some needs real time analytics. A lakehouse allows both to exist together. Earlier, companies copied the same data multiple times. Now, they maintain a single source of truth. That reduces storage cost, pipeline complexity, data inconsistency. Lakehouse is not just storage, it's smarter architecture. But architecture alone is not enough. What happens when data becomes massive? Can one machine process 100 terabytes of data? No. That's where big data frameworks come in. Frameworks like Hadoop and Spark break huge data sets into smaller chunks and distribute the work across multiple machines. Imagine lifting a truck alone. Impossible. But if 100 people help, the work becomes manageable. That's distributed computing. Think about Flipkart Big Billion Day. During Flipkart sales, millions of users search, order, and pay simultaneously. Inventory updates, recommendations, price systems, everything runs on distributed processing. Now think of banking fraud detection. Banks process millions of transactions daily. Now imagine checking fraud manually. Impossible. Spark helps process huge transaction streams quickly and identifies suspicious activity in near real time. Let's compare Hadoop versus Spark. Hadoop was revolutionary, but it relied heavily on disk storage. Spark becomes faster because it processes data in memory. That's why Spark is heavily used today. Big data is not about having huge files, it's about processing data efficiently at scale. Now we know how to process data, but where do companies run these systems? When you book an Uber, do you want the driver location tomorrow? No, you want it instantly. But when your bank sends monthly statements, does that need to happen every second? No, exactly. That's the difference between batch processing and real time processing. Batch processing means data is collected over time and processed together. Examples: payroll systems, daily reports, monthly statements, sales summaries. The focus is efficiency, not immediate speed. Think about Amazon. Amazon may process an entire day's orders overnight. Revenue calculations, inventory updates, business reports, all processed in batches. Think about real time processing. Real time processing is different. Data is processed immediately as it arrives. Example: Uber tracking, Swiggy delivery updates, fraud detection, stock market systems. The goal is low latency. Think about Swiggy. When your order moves, you instantly sees updates. That's streaming data. Data flows continuously and systems react immediately. This is where Kafka and Spark streaming become important. Kafka manages event flow, Spark streaming processes events in real time. Batch gives efficiency, real time gives immediacy. Modern companies use both together. Now, where do companies run all this infrastructure? Now let's move into one of the biggest shifts in modern technology: cloud data engineering. But before cloud, companies had to build everything themselves: physical servers, huge data centers, network teams, hardware maintenance. And if traffic increased, they had to buy even more servers. Now think about this. Would companies prefer spending crores buying infrastructure or paying only for what they use? Obviously, pay only when needed. And that's exactly why cloud computing became so powerful. Cloud changed everything. Instead of managing hardware, companies started focusing on data and applications. And when we talk about cloud, one of the biggest names you will hear everywhere is AWS, Amazon Web Services. AWS provides ready made cloud services for storage, processing, analytics, streaming, security, basically everything needed to build modern data platforms. Now let's understand this using a real world flow. Imagine an e-commerce company like Amazon. Millions of users are placing orders, searching products, making payments, writing reviews. Now, where does all this data go? First, the data lands in S3. S3 is AWS cloud storage. Think of it like a massive cloud based data lake. CSV files stored in CS3, application logs stored in S3, images stored in S3, transaction data stored in S3. Can S3 scale to petabytes of data? Yes, absolutely. That's why companies heavily rely on it. Now, after storage, do we directly use raw data? No, exactly. We need ETL pipelines. Only in AWS, one common ETL service is Glue. Glue helps us extract, transform, and load data. Suppose customer transaction data has missing values, duplicates, wrong formats. Glue can clean and transform the data automatically. But if data becomes huge, terabytes, petabytes, massive distributing processing, that's where EMR comes in. EMR allows companies to run Hadoop, Spark, big data frameworks without manually managing clusters. Imagine processing billions of customers' clicks from Amazon. One machine cannot handle it. So Spark distributes the processing across multiple machines. Big data is not processed by working harder, it's processed by distributing smarter. Now, once data is cleaned and processed, business teams want insights, dashboards, reports, KPIs. That's where Redshift comes in. Redshift is AWS cloud data warehouse optimized for analytic queries. Examples: top selling products, monthly revenue, customer trends. All this is analyzed using warehouse systems like Redshift. Now let's make things more interesting. What if data is coming continuously? Live transaction, IoT sensors, Swiggy delivery tracking. Can we wait till tomorrow to process it? No, that's where Kinesis comes in. Kinesis handles real time match streaming data. Example, live location tracking, real time fraud detection, stock market events, IoT devices. Now imagine everyone in a company gets full access to all data. Dangerous, right? That's why we need IAM. IAM controls who can access what, permissions, rules, security policies. In enterprise systems, security is not optional, it's critical. So now connect everything together: raw data, S3, Glue, Sparks, processing, Redshift analytics, dashboard and insights. Now tell me, is AWS just cloud storage? No, exactly. AWS is a complete cloud data engineering ecosystem. Storage, processing, streaming, analytics, security, everything works together. Now, AWS is one major cloud platform, but many enterprises also heavily use Microsoft Azure. Azure is extremely popular in enterprise companies, especially in banking, healthcare, manufacturing, insurance, large corporate organizations. Why? Because many enterprises already use Microsoft ecosystems. Windows, Office 365, Active Directory, SQL Server. So Azure integrates very naturally with enterprise systems. Now, the interesting part is even though AWS and Azure use different service names, the architecture concepts are almost the same. And this is very important lesson for data engineers. Let's start with storage. In Azure, ADLS, Azure Data Lake Storage, acts as the cloud data lake. Example: transaction files, CSV data, logs, images, IoT data, everything can be stored in ADLS. So if S3 was the storage layer in AWS, what is the equivalent in Azure? ADLS, exactly. Now, once the data is stored, we need pipelines, we need movement, scheduling, workflow management. That's where Azure Data Factory comes in. ADF helps move and orchestrate data across systems. Suppose every night customer transactions data move from ADLS into analytics system, ADF can automate that entire workflow. Remember orchestration from earlier. This is a real example of it. And now, what if data comes massive? Millions of rows, distributed processing, Spark workloads. That's where Azure Databricks comes in. Databricks is heavily used for Spark processing, big data analytics, machine learning workloads. Imagine analytics customer clickstream data from millions of users. Databricks distributes processing across clusters, making large scale analytics possible. Modern data engineering is not about one mission, it's about distributed intelligence. Now, after processing, business teams still need reporting and analytics. That's where Azure Synapse comes in. Synapse combines data warehousing, analytics, querying into one integrated platform. Revenue dashboards, sales trends, executive reports, all can be powered using Synapse. Now, what about streaming data? Live transactions, IoT devices, real-time app events. Azure handles that using Event Hub. Event Hub manages real-time event ingestion at massive scale. Example, smart devices sending sensor data, real-time banking transactions, app telemetry events. And finally, security. In enterprise systems, authentication access controls are critical. Azure AD helps manage user authentication, access permissions, enterprise security policies. Should every employee access production data? No, exactly. That's why identity and access management is critical. So now let's connect the full Azure ecosystem. Raw data to ADLS to data factory pipeline, then Databricks, finally into Power BI dashboards. Now let me ask you something important. Do AWS and Azure work completely differently? No, exactly. The names change, but the architecture concepts remains the same. Storage layer, processing layer, streaming layer, security layer, analytics layer, every cloud platform follows similar engineering principles. Uh, Great data engineers don't just memorize tools, they understand system because tools will change, but architecture thinking stay forever. Now that we understood cloud ecosystems, let's move into one of the most important modern pipeline architectures, Medallion architecture. So now we understand modern cloud ecosystems, we understand storage, processing, streaming, analytics. But here's the next challenge. How do companies organize all this data properly? Because real world pipelines are never built randomly. And that brings us to one of the most important modern data engineering concepts, Medallion architecture. This architecture helps companies organize data, improve reliability, maintain quality, and build scalable pipelines. Medallion architecture organizes data into three layers: bronze, silver, gold, and each layer has a specific purpose. Let's start with bronze. Bronze stores raw untouched data, no major transformations, no business rules, just raw ingestions from source systems. Examples: application logs, raw orders, website clickstream data, IoT sensor events. Now tell me, should we directly build dashboards on raw data? No, exactly. Because raw data can contain duplicates, missing values, incorrect formats. So, what do we do next? We clean and standardize the data. That becomes the silver layer. In silver, duplicates removed, missing values handled, formats standardized, data validated. Example: customer names standardized, data formats corrected, invalid records removed. Silver transforms messy data into trusted data. Now, finally, business team needs insights, KPIs, dashboards, reports. That's the goal layer. Examples: revenue dashboards, customer retention metrics, sales reports, executive analytics. Which layer powers dashboards? Gold, exactly. Let's connect this using Amazon. Bronze, raw customer orders. Silver, cleaned and validated orders. Gold, revenue analytics and business dashboards. So the same data evolves from raw information to business intelligence. Bronze stores, silver refines, gold creates business value. Now let me ask you something. Who actually runs all these pipelines every day? Who schedules them? Who monitors failures? Who ensures dashboards refresh every morning? That's where orchestration comes in. Orchestration is basically managing workflows, scheduling jobs, monitoring pipelines, handling dependencies. Think of orchestration as the brain coordinating the entire pipeline. Suppose every night at 2 a.m., sales data must load into dashboards. First, data lands in storage, then ETL runs, then warehouse refreshes, then dashboards updates. Now imagine one step fails, should the next step we still run? No, exactly. Orchestration tools manage all this automatically. Popular orchestration tools include Apache Airflow, Azure Data Factory, AWS Step Functions. Pipelines are not just built, they must be scheduled, managed, and monitored reliably. That's orchestration. So now let's connect everything together. Lakehouse gives us unified architecture. Big data frameworks help process massive data sets. Batch and real time systems handle different types of workloads. Cloud platforms like AWS and Azure provide scalable infrastructure. Medallion architecture organizes data into reliable layers. And finally, orchestration makes the entire pipeline automated and dependable. This is how modern data systems are built, not just with coding, but with architecture, scalability, reliability, and smart engineering decisions. And this is where what separates someone who only knows tools from someone who truly understands data engineering. Because tools will evolve, technologies will change, but strong engineering thinking will always stay valuable. And with that, we come to the end of Data Engineering Masterclass. Thanks for being part of Product Tech Academy. If you found this session valuable, make sure to like the video, subscribe to the channel, and share it with your friends or anyone who wants to grow in tech. We'll also be bringing more masterclass videos on data modeling, AWS for data platforms, Python, SQL, and data architecture, and Gen AI and agentic AI. And I'll see you in the next video. Till then, bye bye. Take care.